The cause and effect matrix illustrates the relationships between the negative influences of the input, xi, and the process, xp, on the outputs, thus causing the problems y. The results of this tool are also based on the opinion of experts. As one result, the cause and effect matrix gives an overview to all negative influences and the problems they potentially trigger. This image of some specific critical situations in our company is modeled within the theoretical framework of the process problem-solving model, and it prepares the formulation of statistical hypothesis y is a function of x. Another result is the prioritization of influence problem pairings. If the collection of data from influences and problems in your processes is expensive, or if there is a multitude of x's and y's, then the prioritization helps to focus on the vital x-y pairings for an efficient collection of only relevant data. According to these basic ideas, you will find the problems in the columns and the influences in the rows. The problems are visualized in the top cells of the columns. Here you will find the problem y1, cookies bake, taste crumbly insipid, a must be with a severity of 92%. The problem y2, cookies delivered 1 hour too early or too late, belongs to the more or less is better category and has a severity of 60%. The third problem, y3, cookies boxed consumption of energy and ingredients, also violates a more or less is better requirement and has a severity of 60%. The influences of the input xi and the process xp are opposed in the rows of the matrix. Here you find the negative influences of the request for cookies xi1, the start signal xi2 and the tin xi3, as well as the negative influences of the process xp. It might be helpful to involve your experts of the process and ask them, how strong is the impact of the negative influence of the first input xi1 on the problem of the first output y1? Their task now is to evaluate the strength of the relationship between the influences and the resulting problem in the intersection of rows and columns. Thus, the experts estimated the probability at 90% that the weight of the chocolate in the ingredients caused the problem of a crumbly insipid taste. And the experts rated the probability at 100% that the taste of the cookies baked decreases if the chef eats the already weighed chocolate from the ingredients. If the relationship between an influence and a problem is deterministic, that is, if the problem always occurs if the influence is given, then enter 100%. If there is no influence at all, then simply enter nothing. It is obvious that, for example, influences on the availability of an input will more likely trigger availability problems of the output than problems of consumption. In the last columns, the potential impact of each influence xi and xp on all outputs y and the ranking of the impact of each influence are calculated, so that you can see what your most important influences are. In the last cells of the rows, the potential determination of each output by all related influences is calculated. The ranking of the determination of each output indicates which problems are well determined by the listed influences. Maybe you find problems with a low rank for which you did not yet find an influence. If so, you might go back to the input and process analysis to look for specific trigger of this problem. As you can overall see, all important information about the process and its negative impact on the output are logically structured and numerically evaluated. Thus, the cause and effect matrix becomes the center of the measure phase and the core of your project. The chart cause and effect heat map summarizes the information of the cause and effect matrix. It displays the risks of the influence problem pairs in the cells of the matrix. Each risk results from the combination of the probability of the occurrence of an influence, the severity of its caused problem, and the strength of the relationship between influence and problem, also evaluated as the probability that a certain influence causes a certain problem. These risks can vary in a range between 0 and 100%. If you zoom outside of this table, you will get an overview of all risks in your process. Please note that the red fields indicate risks higher than 10%, the yellow fields indicate risks between 1% and 10%, and the risks of the green fields are below 1%. These risks are the basis for a hypothesis. They serve to prioritize the corresponding hypothesis between X and Y. Thus you can easily decide which hypothesis you want to further investigate and thus which data you need to collect. Before we proceed to the hypothesis and the associated data collection plan, let me introduce some notes about the scale levels of measurements. The scale level of a measurement determines the selection of the appropriate graphical charts, process capability indices, control charts, and appropriate statistical tests. If we want to measure the degree of influences and the size of problems, we need to set up a data collection plan. Within a data collection plan, the type of scale that underlies the data needs to be specified. This is necessary because all statistical calculations, charts and tests require data on a certain scale. 3 scales are important: nominal scale, ordinal and cardinal scale. The first differentiation concerns the type of attribute we want to measure. There are qualitative and quantitative attributes. These types of attributes differ according to the values they can take. Values can be attributive, discrete or continuous. Attributive values can be assigned to different categories, like gender with the 2 attributes male and female, or several types of cookies like chocolate, vanilla and cocos cookies. Similarly, we can differentiate types of errors if cookies are insipid, burnt, salty or crumbly. The scale on which the certain values are measured is the nominal scale. The parameter of central tendency is the mode. The parameter of scattering is not important. If you want to measure quantitative, discrete, rank-ordered values, then you can do this on an ordinal scale. School grades and the rating of satisfaction are examples for this scale. All values on this scale are rank-ordered, but we do not know the length of the intervals between 2 adjacent values. Thus, for German school grades, for example, we know that a grade 1 is better than a grade 2, but we do not know and cannot measure the difference between these grades. For the ordinal scale, the parameter of central tendency is the median, and the parameter of scattering is the range, especially the interquartile range. Well known is the cardinal scale. If your attribute can take discrete values, like the number of vanilla cookies or the number of defects in chocolate cookies, or can take continuous values like grams for the weight of cookies, kilowatt hours for electricity or minutes for the processing time, then you measure on a cardinal scale. The parameter of central tendency is the mean, and the parameter of scattering is the standard deviation. The higher the scale level of your measurement, from nominal to ordinal and cardinal, the more information your data carry. This information is reflected in the associated statistical parameters. With this knowledge, we can now proceed to the data collection plan. Let us now specify what exactly we want to measure. This procedure is called operationalization. In the data collection plan, all outputs and their problems, as well as their inputs and activities with their influences, are listed. The problems are ranked according to their severity, and the influences according to their probability of occurrence as calculated in the cause and effect matrix. The first question is, what should be measured? Please specify here in everyday language what you want to measure to capture the selected problem, respective the focused influence. For Y1, we want to measure the taste of cookies. Next, we identify the appropriate measurand. To measure the taste of cookies, we could use a rating scale. The related unit of measurement we want to use are school grades in a range from 1 to 6. Now the target and specification limits can be specified. We want that our cookies are rated close to very good, 1.5, and the lower specification limit is a grade of 4. The question, which different values can the measurand take, serves to determine the scale level of the measurand. The scale level of the rating scale is ordinal. Optional in this list are additionally the nominal scale with data in 2 different levels, like gender, the nominal scale with data in more than 2 different levels, like the type of defects of cookies, and the cardinal scale with data of time, weight, or size, for example. Because there are no data collected so far, stored in a database, we have to collect new data. There is no measurement analysis needed here, because we assume that our customers are used to give us a valid and reliable opinion. A good advice for a further differentiation, later in the statistical tests, is to additionally add some blocking or condition variables about the circumstances of your measurement. Time and date of measurement, the supplier or batch number are examples of condition variables. I choose cookie type as blocking variable. Thus we are later able to differentiate the rating of taste between the vanilla and the chocolate cookies. On the basis of the planned statistical test, I calculated that a sample size of 50 is enough, because I only need to identify differences and relationships of a certain degree that have a practical relevance for us. To the contrary, we are not interested to identify very small differences or very low relationships with statistical tests, because this would only have a low practical relevance for our bakery, but it could be potentially identified with a larger sample. In the next fields, you can further specify certain information about the organization of your measurement. After we determined the scale of our measurements, we can automatically derive appropriate charts for graphical representation of the data, the appropriate statistical parameters, procedures to calculate the process capability, appropriate control charts, and one-sample tests. The color green means full recommendation because the underlying scale carries all necessary information. Yellow means that you might interpret the results with reservation because the scale does not completely carry the necessary information. Beside the measurement of our primary problem, I entered additional operationalization for the other problems Y2 and Y3 and specified influences like the amount of chocolate in XP7 measured in grams and the influence of the quality check of our chef, XP8, who eats respective checks the chocolate or not. Thus, all necessary conditions of our measurement are planned and we can proceed to the hypothesis.